Hi, I am Sanjay Patel. In this video, we are going to solve some more problems on Leibniz theorem. We have already solved 3 problems in our previous video, and let us start with the next one, problem number 4. If y is equal to x into log of x minus 1 upon x plus 1, x minus 1 upon x plus 1, then prove that the nth derivative of the given function y, that is yn, is given by minus 1 raised to n into n minus 2 factorial into x minus n upon x minus 1 raised to n minus x plus n upon x plus 1 raised to n. Let us prove this. So here we have the function y is equal to x into log of x minus 1 upon x plus 1. Okay, let us simplify this first. Log of a upon b is equal to log a minus log b. So I will write it as log of x minus 1 minus log of x plus 1. Okay. Now, before we find the nth derivative, let us still further simplify this. So what I want to do is, first I will find the first derivative of this function. So differentiate this with respect to x. So what we get is the next derivative, that is, the first derivative, that is y1, is equal to, there are two functions here, one is u, other is this bracket. So u as it is, okay, and derivative of log of x minus 1 is 1 upon x minus 1 into 1, minus, again derivative of log of x plus 1 is 1 upon x plus 1. And this plus, now this bracket is as it is, and derivative of x is 1, so 1 into log of x minus 1 minus log of x plus 1. Okay. Now this further I want to simplify and write it as x upon x minus 1 minus x upon x plus 1 plus log of x minus 1 minus log of x plus 1. Okay. Still, we do not have any formula for this kind of function, so we'll again use some simple technique and simplify and bring the standard form for finding the nth derivative. So further, I am writing the first two terms only. Here I will add and subtract minus 1. So I can write x minus 1 plus 1 like this upon x minus 1 minus, here I will add and subtract 1 again and write like this, x plus 1 upon x plus 1 minus 1 upon x plus 1. And the last two terms I am keeping as it is, log of x plus 1. Okay. This we can further write as y1 is equal to, separating this denominator, a plus b upon c is equal to a upon c plus b upon c. So what you will get is 1 plus 1 upon x minus 1, and here again a minus b upon c, you can write as a upon c minus b upon c, and there is a minus sign here. So what I will get is minus 1 and minus minus plus 1 upon x plus 1. So separating this denominator will get this plus, again I am writing the last two terms as it is, log of x minus 1 minus log of x plus 1. And let us call this as result number 1. Now if I want to find the nth derivative of the function y, what should I do here is, I should take n minus 1th derivative, because one derivative is already obtained, y1 is already obtained. So if you want to get nth derivative of y, you need to find n minus 1 number of n minus 1 order derivatives or n minus 1 derivatives of this function y1. So what I am writing is, I will write as taking n minus 1th derivative taking n minus 1th derivative, n minus 1th derivative of 1, that is this equation, what we get is yn, because n minus 1th derivative of y1 is yn, or one can write this way also. Let us write one more step. y1 n minus 1th derivative. Here we assume that n minus 1 is greater than 1. So this first term derivative is 0, it is a constant, plus n minus 1th derivative of 1 upon x minus 1 plus, or rather minus 0, because derivative of 1 is 0, plus 1 upon x plus 1 n minus 1th derivative plus log of x minus 1 hence n minus 1th derivative, and minus log of x plus 1, and we have to find the n minus 1th derivative of this also. y1's n minus 1th derivative will be yn, so there is no problem here. And to write this n minus 1 derivatives of 1 upon ax plus b, and this is the n minus 1th derivative of log of ax plus b. And we have derived the formula for both the functions. So let me just mention that formula. We have these two things. Number one, if y is equal to 1 upon ax plus b, if y is equal to 1 upon ax plus b, then its nth derivative yn is given by minus 1 raised to n into n factorial into a raised to n upon ax plus b raised to n plus 1. And secondly, if we have y is equal to log of ax plus b, then its nth derivative yn is given by y minus 1 raised to n minus 1 into n minus 1 factorial, and this is as it is, a raised to n upon ax plus b raised to n. We already discussed that if you want to remember the formula for finding nth derivative of log function, log of ax plus b, just replace n by n minus 1 everywhere in this formula, formula number 1, except at for this a raised to n. So keep a raised to n as it is and replace this n, this n, and this n by n minus 1. So you will get this formula. Now we will apply these two formulas for writing the n minus 1th derivative here. Okay. So from this above step, let us call it result number 2. From 2, what we can write is this, the next step. So this implies, therefore, from result 2, we get yn, okay, y1's n minus 1th derivative is yn. This is 1 upon x minus 1. So ax plus b, where a is equal to 1 and b is equal to minus 1. So this will be minus 1 raised to n into n factorial, a is equal to 1 upon x minus 1 raised to, sorry, I should not write this. What I want is n minus 1th derivative of 1 upon ax plus b. This is the nth derivative of 1 upon ax plus b. So I must replace n by n minus 1 to get n minus 1th derivative. So this we can write as minus 1 raised to n minus 1 into n minus 1 factorial upon x minus 1 raised to n. Then for this term now, it is 1 upon x plus b again, where a equal to 1 and b equal to 1, and we have to find n minus 1th derivative. So using the same formula, what we'll get is this plus minus 1 raised to n minus 1 into n minus 1 factorial upon x plus 1 whole raised to n. Okay. Then plus, now consider this term, log of x minus 1, and we have to find n minus 1th derivative. So in this second formula, we must substitute n is equal to n minus 1. So what I will get here for this n minus 1th derivative of this log of x minus 1 term as minus 1 raised to n minus 2. I am writing n is equal to n minus 1 everywhere. So into n minus 2 factorial upon x minus 1 raised to n minus 1 minus derivative of this, which is n minus 1th derivative. So again we get minus 1 raised to n minus 2. Everything remains same except the function. Instead of x minus 1 we have now x plus 1. So just replacing n by n minus 1 here, so you will get the n minus 1th derivative. Just it's a matter of simplification now. So let us simplify this. So this implies yn is equal to, what I want to do here is first I will take minus 1 raised to n as common, and another thing is n minus 2 factorial from all the terms. So let us write minus 1 raised to n into n minus 2 factorial. So what we get here in the first term, minus 1 raised to n minus 1 is taken as a common factor. So it is minus, and this becomes n minus 1 upon x minus 1 raised to n. Because this n minus 1 factorial, if you take n minus 2 factorial common, because n minus 1 factorial is 1, 2, 3 up to n minus 1, and the previous term is n minus 2. So if you take n minus 2 factorial as a common factor, what remains is n minus 1 here, and plus again taking minus 1 raised to n common, again we have minus sign over here, and this again same as n minus 1 upon x plus 1 raised to n. Plus, what happens about this? It is minus 1 raised to n is taken outside, so minus 1 raised to minus 2, that is plus 1. And n minus 2 factorial is also taken as a common factor here. So for this term, we have only left with 1 upon x minus 1 raised to n minus 1. The same way, minus 1 raised to n is taken outside, and this is minus 1 raised to minus 2, that is plus 1, and minus sign is there. So what remains is 1 upon x plus 1 raised to n minus 1. Okay, and this implies we get yn is equal to minus 1 raised to n into n minus 2 factorial into now taking that terms containing n x minus 1 together and x plus 1 together. So this is one term containing x minus 1, another term is this. This I can rewrite as x minus 1 raised to n, and then other x minus 1 raised to minus 1 I can write in the numerator. So I am writing this term first as x minus 1 upon x minus 1 raised to n. Is it clear? Because this x minus 1 raised to minus 1 you can take up in the numerator, and here minus this I am writing as it is. The first term now I am writing as it is. So n minus 1 upon x minus 1 raised to n. Same way, now I am writing this term 1 upon minus 1 upon x plus 1 raised to n minus 1, this term as x plus 1 upon x plus 1 raised to n, and minus, now writing this term as it is, n minus 1 upon x plus 1 raised to n. Okay, so let us simplify now. So this implies yn is equal to minus 1 raised to n into n minus 2 factorial into, if you combine these two terms, x minus 1 raised to n is a common denominator, so I will get x minus 1 raised to n, and what you have to do is just add the numerator. The numerator is x minus 1 minus n plus 1. So x minus 1 minus n plus 1, and here taking minus n common and LCM is x plus 1 raised to n. What we get in the numerator is x plus 1 minus n, or rather plus n minus 1, because we have minus sign taken outside here, and then what remains is both with plus sign. So this will be x plus 1 plus n minus 1. Okay, so this gives us yn is equal to minus 1 raised to n into n minus 2 factorial into this 1 will be cancelled. So x minus n upon x minus 1 raised to n minus, again this 1 will be cancelled, and you get x plus n upon x plus 1 raised to n. And this is the required result. Hence proved. Okay. Let us go to the next problem now. It is the problem number 5. So in problem 5, we consider another interesting problem like this. If y is equal to 1 upon 1 minus x square, okay, and an is defined as yn of 0 upon n factorial, then prove that an plus 2 is equal to an plus 1 plus an for every n. Okay. So this is something like a Fibonacci sequence recursive formula. Okay. So let us solve this. Here, the given function is y is equal to 1 upon 1 minus x square. Okay. We want to find nth derivative. Here an contains nth derivative of y at 0. So first I need to find nth derivative. We do not have any formula for finding nth derivative directly of such a function like 1 upon ax plus bx plus c. So what we do is, let us take a cross multiplication and write this as 1 minus x minus x square into y is equal to 1. Okay. Then taking nth derivative on both the sides, we get 1 minus x square into y, its nth derivative, and 1 is a constant, its nth derivative is 0 if n is say greater than or equal to 1 in this case. Okay. Now here for the left hand side I am going to use the Leibniz theorem because it is a product of two functions. So the function whose derivative becomes 0 we take as v. This is a polynomial of degree 2, so its third derivative will be 0. So I will take it as v, and the remaining part, that is y, as function u. So applying the Leibniz theorem, what we get here is nc0, let us not write this, nc0 into nth derivative of u, that is yn, into the function v as it is, 1 minus x square, plus nc1 into yn minus 1 into first derivative of v, that is 0 minus 1 minus 2x. So it is minus 1 minus 2x, okay, plus nc2, one less than this, that is yn minus 2, and derivative of this thing is 0 minus 2. So it is simply minus 2. The next derivative of minus 2 will be 0. So we are not adding the other term. So this is equal to 0, and that we are getting here. Let us simplify this. nc0 is 1. So we will get 1 minus x square into yn, and this we can write as minus nc1 is n, so 2x plus 1 into n into yn minus 1, plus nc2 is n into n minus 1 by 2 factorial, and that 2 will be cancelled with this 2, and let us write minus sign here, this minus 2, this minus sign I am writing first. So it is n into n minus 1 into yn minus 2 is equal to 0. Let us call this as result number 1. Now, to obtain the required result, that is an plus 2 is equal to n plus 1 plus an, here you see that we need yn 0. Okay, so we have to find the nth derivative at x equal to 0, and n plus 1 means yn plus 1 at 0 upon n plus 1 factorial. N plus 2 is yn plus 2 at 0 upon n plus 2 factorial. All yn minus 1, yn minus 2 are here. So what I can write is this as taking x is equal to 0 in this formula, taking x is equal to 0, we get 1 minus 0 minus 0, so 1 into yn of 0 minus 2x plus 1. So putting x equal to 0, we'll get minus n times yn minus 1 of 0 minus n into n minus 1 into yn minus 2 at 0 is equal to 0. Okay, as I want n minus yn 0 upon n factorial, yn 0 upon n factorial, let us divide this whole equation by n factorial. So what we get here is yn 0 upon n factorial, then n upon n factorial is 1 upon n minus 1 factorial. Okay, so n upon n factorial becomes 1 upon n minus 1 factorial, and minus n into n minus 1 upon n factorial. So the n and n minus 1 will be cancelled from this one n factorial, and what you will get is n minus 2 factorial. So yn minus 2 of 0 upon n minus 2 factorial is equal to 0. Now according to our formula, this an is equal to yn 0 upon n factorial. So I will write that. Let us call this as result number 2, and but we have an is equal to yn 0 upon n factorial, okay, for any n. So from 2 we can write the first term as an and minus this term as an minus 1 and this term as an minus 2 equal to 0. Okay, so this can be written as an is equal to an minus 1 plus an minus 2. Okay, so that is the thing. You can replace n by n plus 1 and rewrite this as an plus 2 is equal to an plus 1 plus an. Just replacing n by n plus 2, and then we'll get the required result, that is this thing. Okay, fine. So this completes this problem. Now let us go to the next problem, which is again this was the problem number 5. Let us go to the next problem number 6. So problem number 6. Obtain the nth derivative of x raised to m plus n, where m and n are natural numbers, and in two different ways, and prove that MC0 into NC0 plus MC1 into NC1 plus and so on plus MCN into NCN is equal to M plus N CN. Here we assume that M is greater than N. Okay. And hence we can derive from this, let me write this way. Hence prove that NC0, or let me, okay, NC0 square plus NC1 square plus and so on, putting M is equal to N, what we get is this interesting result. NCN square is equal to 2NCN, and 2NCN we can write as 2n factorial, okay, upon n factorial into 2n minus n factorial, that is n factorial square. Okay, so let us prove this. What is asked is differentiate this in two ways, x is to m plus n, that is the given function. So we have y is equal to x raised to m plus n. This is the function given. Now we'll try to differentiate this in two ways. Now what are these two ways? First, we can use the formula of y is equal to ax plus b. We know that if y is equal to ax plus b raised to m is given, or let me write say k here, then its nth derivative yn is given by say k factorial upon k minus n factorial into ax plus b raised to k minus n. Okay, where k is positive integer, and we have m is means the power n is less than k. Nth derivative is less than the value of k. So here, therefore, for the function y is equal to x raised to m plus n, we have k is equal to m plus n. So what I will get is its nth derivative yn is given by m plus n factorial upon m plus n minus n factorial into x raised to, because the function ax plus b is x only, k, that is m plus n minus n. So this implies the nth derivative of the given function x raised to m plus n is m plus n factorial upon m factorial into x raised to m. And let us call this as result number 1. Now we'll differentiate the same function y is equal to x raised to m plus n in a different way. So next step, now for y is equal to x raised to m plus n, I am considering again, we can write y is equal to x raised to m into x raised to n. Okay, and then taking nth derivative both the sides, so yn is equal to nth derivative of the product of these two functions. Okay, so one function I will take as u, another as v. Here both the functions are simple polynomial, so like anything we can take as u or v. Let us take this function as say u and this as v. So this implies we get yn is equal to, on the right hand side we will apply the Leibniz theorem for this product, So I can write it as say nc0 into un v as it is plus nc1 un minus 1 into v1 plus nc2 un minus 2 into v2 plus and so on plus ncn into u into vn. Okay, now let us call this as say number 1 or temporary, and now let us recall the formula how to write this un and v1 v2 v3. Here we have u is equal to x raised to n, so its kth derivative is given by say n factorial upon n minus k factorial into x raised to n minus k if n is greater than k. Okay, and the same way we can write down the nth derivative of v. Okay, and for v is equal to x raised to, which is m, we can write its kth derivative, say vk, as m factorial upon m minus k factorial into x raised to m minus k if m is greater than k. So now from this kth derivative we'll write un minus 1 and so on. So let us start with say here un, that means nth derivative of x raised to n, which is n factorial. Okay, then un minus 1, that is given by putting k equal to n minus 1 in this, so n factorial upon n minus 1 factorial, that is 1 factorial. So I will get n factorial into x raised to here n minus 1, so it is x raised to 1. Then un minus 2 is obtained by putting k equal to n minus 2 here, so n factorial upon n minus 2, that is 2 factorial. So n factorial upon 2 factorial into x square and so on. Finally we will get say u1 as the first derivative of this thing, or you can write from this formula n factorial upon n minus 1 factorial into x raised to n minus 1. By putting k equal to 1 you will get u1. Also we can write vn for this function. Vn is equal to m factorial upon m minus n factorial into x raised to m minus n. By putting k equal to n here, we will get the nth derivative of x raised to m. Okay, and now putting all these values in this result 1, we get from 1 yn, 1 implies yn is equal to nc0 into un, that is n factorial, into v, and v is x raised to m, plus nc1 into un minus 1, which is this, so it is n factorial into x into v1. v1 means first derivative of v is equal to x raised to m, so it is m times x raised to m minus 1 plus nc2 into this thing un minus 2, which is n factorial upon 2 factorial into x square, into the next derivative of this function, which is v, as m into m minus 1 into x raised to m minus 2, plus and so on. The last term we can write as ncn plus ncn into u, simply the function u, that is x raised to n, into Vn. Vn is given by this. So I will write it as m factorial upon m minus n factorial into x raised to m minus n. Now if you observe that in this we have n factorial as a common factor in all the terms, and what else is x raised to m is also common. So n factorial, x raised to m is here, and this x and this x raised to m minus 1 will give you x raised to m. So I can take x raised to m and n factorial as a common factor. What remains is nc0 into 1 plus, for the second term, nc1, n factorial x raised to m goes out, so we'll get only m plus nc2, and again x square and x raised to m minus 2 gives you x raised to m, that is written outside, and this n factorial is also taken out. So m into m minus 1 by 2 factorial plus, and so on. Last is ncn. Again, this x raised to n and x raised to m minus n gives you x raised to m, and that n factorial we can write as, let me check there, Vn, putting k equal to n is fine. Okay, so we get here m factorial upon m minus n factorial. Okay, and let us multiply and divide by n factorial. So there is no n factorial here, so I'm writing 1 upon n factorial like this as the last term. So it's a tricky one, and this I can rewrite as, this implies yn is equal to n factorial into x raised to m into nc0, and then 1 I can write as mc0 plus nc1, this m I can write as mc1 plus nc2 as it is, and m into m minus 1 by 2 factorial is nothing but mc2, plus and so on, plus ncn, and this we can write as say mcn. mcn is m factorial upon n factorial into m minus n factorial. So we will get this thing, and let us call this as result number 2. Now result 1 and 2 are the same thing because they represent the nth derivative of x raised to m plus n. X raised to m plus n nth derivative is given here using formula in result 1, which is m plus n factorial upon m factorial into x raised to m, and this is given using Leibniz theorem. So we can compare both the results and write, so comparing 1 and 2, because 1 and 2 are the same derivatives of x raised to m plus n. So comparing 1 and 2, we get, left hand side is, I am writing as result 1, m plus n factorial upon m factorial into x raised to m, and the right hand side I am writing this result, that is n factorial into x raised to m into this thing, that is mc0 into nc0 plus mc1 into nc1 plus and so on, plus mcn into ncn. Okay, so now we can cancel these two from both the sides. X raised to m will be cancelled, and taking n factorial in the denominator of the left hand side, what we are getting is the required result. So this gives us m plus n factorial upon m factorial into n factorial is equal to mc0 into nc0 plus mc1 into nc1 plus and so on, plus this. Again, if you wish, you can write this left hand side as this, you can write as m plus n c m factorial Okay, m plus ncm, so it is m plus n factorial upon n factorial into m plus n minus m factorial. You can write m plus ncn or m anything you want. Both are same. And this as mc0, nc0, nc1, nc1 plus and so on, plus this is mcn into ncn. This is m. Okay. So this proves the result, and putting m is equal to n in this, we'll get the next part, that is putting m is equal to n. Here we get 2n cn is equal to nc0 into nc0, that is nc0 square plus nc1 square plus and so on, plus ncn square. And that is nothing but nc0 square plus nc1 square. So this gives us the sum of the squares of the binomial coefficients, and its value is 2ncn, that I can write as 2n factorial upon n factorial into n factorial, that is n factorial square, and that is the required result. So this completes this solution. Let us solve the next problem, number 7. So if f of x is equal to 10x, then prove that fn0 minus nc2 fn minus 2 0 plus nc4 fn minus 4 of 0 minus nc6 fn minus 6 0 plus and minus and so on is equal to sine of n pi by 2. Okay, let us prove. Here the given function is fx is equal to 10x, and 10x is sin x upon cos x. So I can write down this as cos x into fx is equal to sin x. Now we take nth derivative in this, both the sides. So taking nth derivative on both the sides, what we get is here fx into cos x nth derivative is equal to nth derivative of the function sin x. Let us recall what we have studied about nth derivative of sine and cos. We know that if we have y is equal to sine ax plus b is the given function, then its nth derivative in is a raised to n into sine ax plus b plus n times pi by 2. For the left hand side here, I want to apply the Leibniz rule because it is a product of two functions. So one function I can take as u, other as v. Here we can find the derivative of cos x very easily. So let us take this as v, and this function is fx. So we keep it as it is and take it as u. So applying the Leibniz theorem, this implies the first term is nc0 un, that is fnx into the function v as it is, that is cos x as it is, then plus nc1, then 1 less fn, then fn minus 1 of x into cos x derivatives minus sin x plus nc2 fn minus 2 of x into derivative of minus sin x is minus cos x plus, let us write some more terms, plus nc3 fn minus 3 of x into derivative of cos x is minus sin x, so minus minus plus sin x, so plus and so on. Okay, and that is equal to the right hand side nth derivative sin x is obtained by this rule. Here in this a is equal to 1 and b is equal to 0, so its nth derivative is given by 1 raised to n, that is simply 1, and the right hand side will be sine of x plus n into pi by 2, and let us call this as 1. What we need is these terms fn0, fn minus 2, 0 and so on from this result that says that we have to find the value of this derivatives at x equal to 0. So we substitute x equal to 0 in this. So put x is equal to 0 in 1. So we get nc0 fn0 into cos 0 is 1 plus nc1 into fn minus 1 0 and sine 0 is 0, okay, then plus nc2 fn minus 2 of 0, and this cos x at x equal to 0 is minus 1, so it is minus 1 plus nc3 fn minus 3 of 0 into sine 0 is 0, so plus and minus and so on is equal to sine of 0 plus n pi by 2. So just if you observe that all the odd order derivatives in this are 0 because they are multiplied with the number 0, so this will go and so on. Okay, and for other terms which are even order, that there is an alternate sign here, minus, then it will be plus and so on. So I can write it as nc0 fn0, okay, then this minus sign I am writing here, minus nc2 fn minus 2 of 0. The next term would be plus nc4 fn minus 4 of 0 and minus and plus and so on, and the right hand side is sine of n pi by 2. Okay, and this is the required result. So hence the result is proved. This was the required result. You can see here, this is the required result. So we have discussed some interesting problems based on Leibniz theorem and some special problems also. And with this, we come to the end of this first topic of successive differentiation. Okay, thank you.